Hello, everyone. I'm Effie. I have a bachelor's degree in physics and a master's degree in scientific computing, so naturally I became a sysadmin. I have worked in many small companies, a dead MMORPG game, and since last year, I've been an SRE at the Wikimedia Foundation.
Hi, everyone. My name is Alexandros Kosiaris, and I am with the SRE team at the Wikimedia Foundation for the last 6 years, being a sysadmin before that. I don't know what that says about me. Probably I'm damaged, but you know better. And I'd like to thank Kyle for kind of spoiling a little bit stuff of what we're going to say. Great presentation, by the way.
So today we're going to talk about what happens when you type wikipedia.org, or what happens when you click your first Google result. This is generally a popular interview questions, but we are going to discuss the server side. All information is simplified, and since our goal is to present something that is understandable about a website, we all know what it does. So we will mention a few general information, and then we're going to describe our systems from the inside out, that means the application layer, and then approach this from the outside in, where we'll describe what happens when you're entering our infrastructure. Now, if something we say is all Greek to you, it's expected since we're both Greek. But by all means, come and talk to us later to discuss more details. So, did you know that the Wikipedia infrastructure is run by the Wikimedia Foundation, which is an American nonprofit organization and has no affiliation with WikiLeaks. Wikipedia is an 18-year-old project, thus we're running an 18-year-old software. All content is managed by volunteers, and we host some really unusual articles like list of helicopter escapes or list of people who died on the toilet. Now, sadly, those articles, along with million others, can't be read in Turkey or China. Now, Wikimedia hosts and supports many other projects like Wikicode, Wikinews, Wikiversity, and Wikidata, which is a project run by Wikimedia Deutschland, and it's the central storage for structured data on Wikipedia and sister projects. We are only using open source software, so everything we'll mention here is even in-house developed software is freely available. We have 2 primary data centers in the US and 3 caching points in San Francisco, Amsterdam, and Singapore. We are serving about 17 billion page views per month with a little over 1,300 bare metal servers. So why aren't we not on the cloud? We want to have full control over who can access our data. Consider how important this is to editors in countries where censorship is an issue. And privacy is something we take seriously. Secondly, at this traffic level, it is simply cheaper to own your equipment. And lastly, when this project started, there was no such a thing as the cloud. So the SRE team is a globally distributed team of 26 people responsible for developing and maintaining Wikimedia's infrastructure. We try to follow the 2 pizza rule, so we are divided into smaller teams. The data center operations, the data persistence, the DBAs, infrastructure foundations, the team that is dedicated to tooling and observability, etc. The service operations team, what me and Alex belong to, supporting services like MediaWiki, microservices, Kubernetes, and traffic, which is dealing with our networking, edges, and caches.
So as we promised, we will be talking about our infrastructure from the outside in and from the inside out. So starting first from the inside out, let's talk first about the application layer. And the application layer is a 18-year-old software called MediaWiki, which is essentially a LAMP stack. It's PHP, MySQL, yes, all the stuff that you probably know. And it's our core application. That essentially means that it's also our hammer. And if you have heard the saying that when you have a hammer or your problems look like nails, yes, we are guilty of that. And we have used it for pretty much everything. And that has a couple of interesting implications that it would be nice to talk about. We have a variety of clusters that are essentially all MediaWiki clusters, but we just route different requests to them. So we have the app service cluster, which is a cluster that all of you guys interact with whenever you're visiting a page, as long as that page is not cached. And we have an API cluster, which is what most editors interact with, because we now have a what you see is what you get editor, that is a visual editor, that's how we call it. And that's when you interact with API cluster. And then we have a cluster that is, these days it's called job runners / video scalers. It used to be different clusters, but we merged them. And essentially MediaWiki is being spawned up in order to run a variety of jobs that we have. One of these, that's why it's called also the video scalers cluster, is to go around and resize and recode into various open formats and codecs the various videos that are uploaded into Wikimedia Commons. One interesting thing that I'd like to note here is that we used to be PHP only, then we went to HHVM because of latency and performance reasons. Turned out it was a really interesting journey. And for a few years it was great, and then Facebook decided that HHVM should no longer support PHP and they all should only support Hack, and we had to go back to PHP. Again, the reverse interesting journey, and since a few days ago we're now fully PHP 7.2 compliant and only run that, no HHVM anymore. And so you'll be asking yourselves, how is it that a LAMP stack is possible of serving that kind of traffic? And the answer is caching, 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 caching. So as you can see in this graph, we have four different caches. Starting from the inside out again, next to MediaWiki in this beautiful diagram drawn by Effie, we have the op cache and the APCU cache, which is if you ever had to interact with PHP before version 5.5, it was all called APC, essentially compiling the operations that PHP code is into bytecode instructions that you could run just in time on the various application servers, Apache essentially. And these days it's split into those two caches, op cache and APC cache, and they do the exact same thing that they used to do back then. And then on the right-hand side, we have Redis, where we store our sessions, alongside a lot of stuff that is pre-rendered for various pages. And we use a software called Nutcracker. It also used to be called TWM Proxy, and it's written by Twitter. And what it essentially does is it allows MediaWiki to talk via Unix socket to the entire fleet of the various Redis databases, and also performs health checking. It does Ketama hashing algorithms in order to split the various keys and distribute them across the fleet, and all that interesting stuff. It also used to drive the memcached fleet that we have, but we now migrated to a software from Facebook, so we lost HHVM, but at least we got MacRouter. And MacRouter has one extra very interesting key ingredient that we have. It allows us to duplicate our caches and our sessions across data centers so that we are able to deploy an entire data center in case that something goes really wrong. Now, all of these, I'm pretty sure you've seen them before. They're essential ways of going around and storing parts of an entire page of parts of a page, and that's what we mostly do. But we also have that thing on the top right, on the bottom right, the parser cache. So if the icon looks like a database, it's because it is. It's a MySQL, a table with one row, with two columns, key, value. So essentially key value store, that goes around and stores pre-parsed versions, entire pre-parsed versions of the pages. So in case all of the other caches fail, then we are able to quickly serve the page to the users. And to give you an idea, the Barack Obama page, which we've been using as a benchmark for years, takes 10 seconds to parse from scratch. So that thing over there, it can really help us in cases of real heavy load. As I said before, hammer, nails. So we are now trying to move away from that, and we're moving into SOA, service-oriented architecture approach. So back in 2014, we came up with this thing that you see on the top right, and it's called Parsoid. So MediaWiki had, and still has, this parser inside that transforms the language, the DSL that we have from Wikitext to HTML, but it's unable to do the inverse. So when we had to create that, what you see, what you get editor that I talked about earlier, we needed something that was able to do the inverse, and that's Parsoid. So you have those two paths in that service, and it has served us nicely for the last 5 years. But along those 5 years, we went from those two, the huge hammer that we used to have MediaWiki and Persuade, into those more than 10, that you can see that in beautifully hand-drawn word cloud. By the way, if you're interested about that font, it's her handwriting, okay? And we have that word cloud with all the various services that we have. And we've been moving along in trying to make MediaWiki less of a huge monolith, and that would allow us to move faster and all the other interesting things that an SOA does for you. But we also moving to that because we also wanted to gain elasticity. As you can guess, since we're all bare metal, those MediaWiki hosts that we're talking about are all they're very strictly set up and set in numbers, really like hard in stone almost, how large they are. We are able to add capacity, but it takes time because you have to procure hardware. So the move to microservices alongside with adopting the current standards in the industry, things like Kubernetes, for example, which I'm going to talk about later, allows us to add elasticity. It also allows us to have hardware full migration, deployments, which are going to be an interesting thing that I'll talk about in the next slides. And I can tell you that the migration, as you can see, it's taken already 5 years. It's not at all done. It's not easy. It's still ongoing, and it's painful. And since I mentioned that, we showed you that word cloud with the various microservices, let's see 4 of them, just the most interesting ones, at least in my personal opinion. So, first one, in case somebody wanted to infer that, yes, we used MediaWiki in order to do image scaling, which is not really great. But now we have Thumper, which is a software not written by us. We have contributed to it, but it's software we adopted, and it's great, and it's now being used for image scaling. And it works quite well. We have a software that's written internally that's called Mathoid, and it renders LaTeX. From LaTeX, it returns the various JSON, PNG, JSON, SVG, JPG representations of various math formulas. If you've ever interacted with a Wikipedia page that has a math formula, you've interacted with that service, directly or indirectly. We have a service called ORS that is being used to help anti-vandalism efforts. Whenever somebody shows up and tries to vandalize a page, they get scored by this machine learning thing, which is statistically giving them a probability of being good or bad or whatever, and it helps editors revert changes. And finally, there's a mobile content service. If you have a Wikipedia app on your cell phone, you probably interacted with it directly because it modifies the page coding on the fly and turns it from this rather old DOM that we have to a friendly for mobile devices DOM. So as already mentioned, we adopted Kubernetes. And by the way, all of the images that we have, they are from Commons and they are CC by SA. And we chose that Helm because it means Kubernetes usually, but we also because we adopted Helm as well. And how is our Kubernetes installations structured? Again, bare metal. And we go through the entire way of setting them up on our own. And that means no kubeadm, no kops, none of these tools. We just use Puppet and Debian installer in order to get the machines running PXE and all. And after that, we get, and it's one touch. We don't really have to do much about it. And we have a new host that's able to work out as a Kubernetes node. We use Calico as our CNI plugin because after evaluating the various CNI plugins, it turns out that Calico was the best fit for our network at the time. We're adopting Helm for deployments, and let me tell you that it's been a really interesting thing because, as I'm pretty sure a lot of you have done, we had developed our own tool for deployments in-house. It was called SCAP. It is still called CAP. It has gone through 3 different versions, and it's at times challenging to use it. And using Helm has allowed us to move faster in deployments, having better deployments, having blue-green, having canaries, things that we don't really yet have with SCAP. Our clusters are 3 currently. We have 2 for production, 1 per primary data center. Effie will tell you more about that later on, and a staging one because we wanted to be able to stage our applications before going through with updating in production. Docker is our CRE, container runtime engine that is, but we would like to, we are evaluating others like CRI-IO. We would like to have some POC at some point, some proof of concept with one of those. Anyway, this is an ongoing process for the last 2 years. 11 services are on it. The mathematical thing that I was talking about earlier is on top of Kubernetes, and pipelines in the works, it's about 90% complete and works great. So this is a slow journey, but it has been interesting, and we have reaped some benefits from it. And let's go on to our message queuing. And this is the place where we're going to see some interesting things that can happen in Wikipedia. So message queuing-wise, we adopted Kafka a long time ago, about 6 or 7 years. And the reason was the analytics team that we had back then wanted to be able to run analytics with a confidence that they have not lost packets or page views from users. Fast forward a little bit, and the software proved itself, and the rest of the organization started adopting it for other reasons. So it's our one message queue to rule them all right now. And what we use it for, we use it first for things like Wikitext templates refresh. And now you're going to ask me, what on earth is that? So whenever you have gone into a Wikipedia page and you see that info box on the bottom, on the right-hand side of the page, things like going to a city, and it has things like population, area, or like a person, date of birth, date of death, if one exists. This thing is a template, which means it's a thing that you can call from any other wiki page, and it will allow you to do not repeat yourself. It will allow you to include stuff very easily. But the thing is, those are editable as well. So when somebody edits a template that is being used across thousands or tens of thousands of pages, all of these pages need to be reparsed, and the edges need to be purged, because otherwise people will be getting stale data. And as we know, there are 2 problems that are difficult in computing. One is naming, and the other one is cache invalidation. So that's where we use Kafka as well. There is also things like cross-wiki links. For example, Wikidata that Effie talked about earlier is able to be referenced from Wikipedia. And the same thing with Commons, which is our repository for various media. And we also have things like informing the system that it needs to create new thumbnails, it needs to recode videos. All of these use Kafka underneath. The job runners and all are all MediaWiki or various other services, but still Kafka is what powers the message moving. And from that, I'll pass back to Effie.
Now, let's talk about the darkest dungeon of every infrastructure, which is run by our lovely dungeon masters, the DBA team. We are using MariaDB, and for some complicated reasons, we switched from MySQL to MariaDB in 2013. Our database classes are divided into sections, and each section has a master and many replicas. Think of sections as a statically assigned sharding mechanism. As you may have guessed, MediaWiki reads from replicas and writes from the masters. We have 3 main clusters, the Wikitext one that holds the actual Wikitext in blobs, the metadata one, which tells MediaWiki where Wikitext is stored, and lastly, parser cache that Alex explained, where we store rendered pages. Now, we do online schema migrations, so alter table starts from the replicas and can take weeks to complete. We do cross-database replication, cross-data center replication, and according to this diagram, say section 1 in Encrypt has DB1067 as a master. This replicates to 4 replicas, where the 4th is located on another data center, which in turn replicates to its replicas. All our databases use TLS. We are using snapshots for full disaster recovery and provisioning, and dumps for long-term archiving and small-scale recoveries. Our DBAs presented our backup system a couple of days ago at Percona Live in Amsterdam. You can check out the video soonish. We have about 150 database servers serving 350,000 queries per second, and we need about 70 terabytes of RAM to do that. Now, that search box on your top right is Elasticsearch, and searching on Wikipedia is run by a team that is called Search. But this is a different presentation. Moving on to the containers where we store all media that you upload to Wikipedia. We're using Swift, which is a scalable object storage system by OpenStack. It has 2 main features. 1, it speaks HTTP, and 2, it's easily scalable. We just add more servers, and it takes care of replication and indexing and all that. We send requests to the front ends, while the backends take care of storing and retrieving your data. We host about 1 billion objects that add up to about 390 terabytes. Good. Let's see what happens when you hit our servers from the outside to find what happened when Sweden switched driving from left to right in 1967. This is where this picture is from. Back to the map. We have 5 DCs which are interconnected using IPsec. The primary DCs hold everything, right? Articles, user data, everything. The caching points just hold static objects and terminate TLS. Now, the reason we do this, the same as Facebook before was doing, it's faster and cheaper to serve you from a server near you than from the other side of the world. Also, we have interconnections with other networks, like your internet provider's provider, or like with Google or Facebook, etc. Now, fun fact 1, readability in Asia increased with the Singapore data center, since latency was reduced by 30%. And before that, Asia was served partially from San Francisco and partially from Amsterdam. Fun fact 2, after the US elections in 2016, we have observed an increased traffic from Facebook. And fun fact 3, we have ping offload servers because people like to ping Wikipedia to check if they're connected to the internet, and that was causing problems. Now, moving on. This is a higher level graph of how you hit our systems. GDNSD will point you to the nearest data center, and some complicated routing magic will take you to our LVSs, which in turn will direct you to our CDN. Now, let's explain all those things. TLS termination layer and the edge caches on all our DCs constitute our CDN. GDNSD is a GeoDNS server where we have assigned each country to its nearest data center, where we are using a very small TTL of 10 minutes that allows us to deploy a data center fast if things go wrong. So if we're having issues in Amsterdam, we can reroute traffic, the European traffic to the United States within 10 minutes. Now, LVS is the Linux virtual server. It's an advanced layer 3, layer 4 load balancing solution for Linux, which support consistent hashing, and everyone is using it. Lastly, Pybal is our in-house LVS manager. It instructs LVS to depull and pull backends on demand, depending on backend health or simply because we need to. Now, this was explained in the previous talk extensively, but the unsimplified description of how LVS direct routing works is that it accepts incoming packets for a specific IP address, and it routes those packets to the target servers, which in turn respond directly via their default gateway. So the goal is to do both load balancing and maximize outgoing bandwidth. Now, we mentioned our own CDN, and it looks like a bit like this. Think of it as an onion with different layers. We have the Nginx- layer, we have the Varnish frontend and the Varnish backend layer, and lastly, the application layer, which discussed earlier. Nginx-, in our case, is responsible for TLS termination, while Varnish takes care of caching. The Varnish frontends store objects in memory, so this is where we find the hotter objects that you're requesting, while the Varnish backends store objects on disk. Those two are also divided into Varnish text, where we store HTML, CSS, JS, etc., and Varnish upload, where we store media. Now, we are in the process of migrating away from Nginx- and Varnish, and instead use ATS, the Apache traffic server. The reasons are beyond the scope for now, but the really short version is that Nginx Plus and Varnish Cache Plus have features that we need and we can't use, like missing TLS termination and Varnish. So we have to migrate away. So as you can see, we are replacing the software, but we are keeping the architecture. Another interesting change that we have kicked off recently is replacing all our certificates with Let's Encrypt ones. To facilitate that, we are using Acme Chief, which is a product, it is a product of a hackathon, actually. And it is an application that handles the whole process of issuing and renewing Let's Encrypt certificates for multiple names using the DNS method. So, putting everything together to see how it works. By the way, this device used to be an offline Wikipedia, which is beyond the scope of this talk. So say we're requesting the Dublin article from Dublin. GDNSD will direct us to Amsterdam, and we're going to hit our edges, our routers and LVSs. Now, Nginx miners will encrypt this connection, and if that URL is cached in Varnish, it will be served back to you. And this is where more than 90% of requests terminate. They terminate in the caching layer. And we're very happy about it. If that URL is not cached in Amsterdam, then your request will be forwarded in Virginia, United States, where we'll check if that URL is cached in the Varnish backends there. Now, if we get a miss there as well, then your request will be forwarded to MediaWiki, which in turn will check memcache for the page. It will check parser cache for the page, for the render page for Dublin. And if there is a miss there as well, if we get a miss there as well, again, it will locate it in MariaDB, retrieve it, render it, serve it back to you, store it on parser cache, store it on memcache, and then the Varnishes will store this as well. Now, interestingly, if you request the media file, Varnish will fetch it for you directly from Swift and not via MediaWiki. Now, when we are editing an article or a template, or uploading a media file, the long and winding road that leads to MediaWiki is the same, but this time we're doing a post request. MediaWiki is going to store your edit to the master DB and of the wiki that you're editing, and then it will trigger many jobs like the ones Alex spoke before. Purge HTTP caches, update dependent pages, re-render pages including that template. And pages can include other pages and so on. Now, if this is a media file, MediaWiki stores its metadata on MariaDB and the actual file on Swift. If that is, and if it is an image file, it will trigger Thumbo to create thumbnails, or if it is a video, the video scalers to encode this to other open source formats. So you can imagine now what happens when someone really famous dies. We have the phenomenon we call celebrity death spikes, or the Michael Jackson effect. Everyone links to Wikipedia to read about them, while a bunch of editors are spiking the edit rate by constantly updating it. And as details about the cause of death emerge, editors are nitpicking each other's changing all the time. And this becomes an unfortunate load problem, as heavy read traffic focuses on an article that is constantly being edited and invalidated from the caches. And over to Alex.
I have a personal request. I know all of you have a similar thing. Our term is Michael Jackson. Please reach out to me later and talk to me and tell me how you call yours. I'm interested.
Show me yours, show you mine. Oh, that's yours.
Oh, it's mine? Oh. So let's see now how we manage with 26 SREs to serve all of this traffic. Because depending on the year, depending on the benchmark, and whether China and Turkey are blocking us or whatever, we're anywhere from between top 5 and top 9th site in the world. So how do we manage with all of that? For starters, we adopted DevOps mindset a long time ago, so infrastructure as code. And that means, in our case, a configuration management system. We adopted Puppet a really long time ago. I think it was version 0.26 or something, or 0.24. And I know lines of code don't mean anything, and that's good. They shouldn't really. But I do have them there in order to give you an order of magnitude of our code. So it's around 50K lines of Puppet code and 100K lines of Ruby and ERB, not of all written. ERB, by the way, is embedded Ruby. It's when Puppet needs to render various templates. So not all of this code is written by us. There is some of it that it's imported, but the majority is indeed written by us. And the reason I'm telling you this is because all of this code needs to be tested whenever we upgrade Puppet versions. And it's a fun trip. And the other thing is that Puppet does not really provide you with a lot of orchestration. It's a good configuration management system with all its quirks and problems and all, but it does the thing it's designed for. However, it does not provide you any kind of with any kind of nice tools for automation and orchestration. And after evaluating various ones, we had to end up developing our own. We call it Kumin. And it is essentially fronted to the Puppet DB. It asks the Puppet database for the various host names based on various predicates. Things like, hey, you know what, I want the Varnish servers that are in Amsterdam and San Francisco. And you get that back, and then it just executes SSH commands in parallel to all of them, using various tricks in order not to kill the entire fleet. Things like sleep after each server for an X amount of seconds, or do 5 servers in a row and things like that. It's pretty useful and interesting, so if you have adopted Puppet and you have Puppet DB, take a look. It's open source, of course. And so we have adopted these two. We have developed one and adopted the other two, but we're also adopting Kubernetes, as was already said. And we are really heavy as it's CI/CD and testing and all that because, well, you can test the code, but you also have to test and get peer reviews and approvals for the various configuration changes. So while we do have an override and we are able to push configuration changes when we really need to, because outage, we tend to try and get approvals and code reviews from other members of the team before pushing forward any kind of configuration changes via Puppet. And in a nutshell, by the way, there are a number of things we haven't touched in this presentation. First is performance. We have said nothing about it, aside from the fact that Singapore provided us with a nice decrease in latency for users. We haven't touched about analytics. It's another team's job. If you're interested, we can send them here to give you a presentation. And observability. But we believe, at least we'd like to believe, that it's possible to run a high traffic site in the internet with only open source software and without an army of engineers. It is challenging, I can tell you that. It requires dedication and passion, but it is possible. And we'd like to think that the solutions that we have presented you here, and which you can all ask us more about, they can be used in smaller environments as well, and that would make total sense. We think that it's fine if those are reused. In fact, we know many of these are reused, like the LVS thing that Effie talked about. We know everybody uses it. And with that, we would like to close with a friendly message from our sponsors, which technically are you. Right? You are viewers and editors. I hope you're editors. And
we are hiring.
We're hiring.
You are hiring.
Thank you very much. We have a few minutes for questions.
Thank you for the talk. As a non-profit, how did you decide which open source license to use for your own tools that you wrote? I saw on a slide you said you used GNU GPL. It doesn't say which version. So how did you make that decision?
Depends on the software. The default is GPL v3. But of course, as long as it's an OSI-approved license, the owner and the writer of the software can choose any of the other ones.
So this is less a question than a comment on LVS. Good choice. Facebook used it for many years.
Was there another one?
Anyone else? Shout if... Oh.
So what do you do about the Michael Jackson effect?
About?
The Michael Jackson effect.
Oh. What can you say about the Michael Jackson effect?
So the Michael Jackson effect happened back in 2009 when Michael Jackson died. And what happened is that the moment that he died, somebody decided to edit the page and add the date of death, and then somebody else had decided to edit the page and add probable causes, and this kept on for a long time. The issue was, of course, that the page was being constantly reparsed, constantly being updated with more stuff, and as I said, the Barack Obama page takes 10 seconds. I have no idea how much the Michael Jackson page takes these days. I'm guessing somewhere in that order. So every time that somebody edited it, we had to go through a really expensive process of reparsing that, and it happened many, many times a second. And of course, viewers were trying to view the page, they could not view the page, or in the best case scenario, they were viewing a stale version of the page, and then they tried to edit it again, just exacerbating the problem. So in order to fix it, what we had to do after, of course, we did all the firefighting and all that, we went ahead and wrote an in-house developed distributed log system called Pool Counter. That is being used by MediaWiki, and it goes around and issues logs on the various pages and the various parsings and all, and says, hey, you know what? No, I'm not going to be reparsing that page again and again and again and again for no reason. So it's essentially a locking mechanism, semaphores and all.
A colleague shared recently that he was in the loo reading the news, and he read that Robin Williams died, and he was like, oh no, and then his pager went off.
Any more questions?
Just a real quick one now. What was the motivation for moving away from MySQL towards MariaDB?
Oh, I'm going to have to ask the DBAs for that. I mean, come and grab me, I can ask them. But I think it's probably a painful story.
Thank you again for the talk. One question I had, you were saying how Obama's page essentially takes 10 seconds to load. Where's the majority of that time being spent? Is it in PHP app layer, database layer?
Sometimes it's because, I mean, if there are templates being used, it's like pulling those templates as well, so rendering that. That is one reason, I reckon.
Yeah, but the biggest one is CPU trying to transform from wiki text to HTML. That's a big one.
Right.
And if you go to the Barack Obama page, it's a large page. It's not a small one. We have worse. I can tell you that tables can be really interesting to parse at times. And thankfully, Barack Obama page doesn't have many, but there are users out there in the sandbox who have managed to create pages that take many times more than the Barack Obama page to parse, because they are doing weird things.
But we have had cases where some editor changed a template and it nearly broke the whole Wikipedia. Yeah, I know.
I'm sure people want to know more about this. Any more questions? If I don't see you, just shout. Okay. Thank you very much.
Thank you.